Okay, so any questions over homework? This is not what I expect. Yes?
3.3, number 40, 44. We did 39 from there, which was kind of similar. It was like sign limit as x approaches 0.
Oh, yeah.
But I struggle with the other two.
I understand. So this one says number 40's got who's on the top? 4x. Now, real quick, little side note. So we know that this limit is 1. What is that? What do you think that means? This limit is 1. No way. It's crazy. All right. Is it cool? That only makes sense. So, what is that guy missing to make it look more like something we know? 4x underneath it, right? And what's that guy missing to make it look more like what we?
A 6x.
6x up top. So I can actually multiply top and bottom by x and not have to worry about. I mean, there we go. And why am I allowed to do that? I would only not be allowed to multiply top and bottom if x was 0, and this is a limit as x goes to 0. So is it ever 0?
No.
Hell no. So I'm completely allowed to do that. And the only reason I'm doing that is because this is missing that kind of thing. But now, what number needs to be here?
6.
So here's the cool thing. Put a 6 there. The minute I put a 6 there, what do I have to put on the outside? Where? To balance that out? Down there. So incredibly enough, I would need to put a what here?
4.
4. And then over here I put a 4 on the top. So overall, I just did nothing. Right? I just made it look different. How are we doing so far? Is this?
Yeah, that's what I was doing. Or that's how I started it.
Sweet. Good.
Alright.
So then what's this guy's limit here? 1. What's this guy's limit here? So this is 4 6 times 1. 2/3. Right? You can always graph sine 4x over sine 6x and see what happens.
Because the other Monday, it was like sine of 3x on top and then x.
Yeah, so that one was sort of the
I took a
same.
guess and I just guessed 3 because there was just a 3 on top and cancel the x. Is that always going to be like that? Because that was like 4 6.
Yeah, the
If
idea
it was sine 5x over or under sine 8x, would it be 5/8? You know what I mean?
Yeah, now you can make the pattern. Now you can figure out, and the whole thing that actually governs this. If I look at this from the beginning, and this is not really the way I want you guys to do this, but you start to realize at the heart of this is what I said before. When x gets really small, sine of x is approximately what? X. If you just solve that for sine x, you get sine x is x. When x is really small. So x is getting really small, so sine of 4x is approximately 4x, and sine of 6x is approximately 6x. That's 2/3 all day long, right? And same thing here. That's approximately 3x. 3x divided by x is 3. That's why, that's 3. But it's the difference between, right now I want you to really see where things are coming from and why that really works. Because that's not quite rigorous enough. But if you were in a physics class and you had to do this limit real quick to do that, I wouldn't do all this mess. I would just do that. Right? That's the quick way to get there, because it's exactly the same idea, just hiding a little bit of why it works. Is that cool? Okay.
I understand that, and that's what I was thinking, so I got 2/3. But I just wasn't sure if I did it right.
But this is the way to really show all the work.
Right.
Right there, yeah. Cool.
But 44, can you do that one real quick? That one's a little, or just explain what the difference would would be.
The difference, the beautiful thing there is, what is sine of 3x and sine of 5x? Those are both missing something x on the bottom, but they actually have it. They gave you two x's on the bottom, right? Split them up.
Oh,
X,
okay.
X. And then you give the numbers in there, and that one flows really nicely. Okay. Anything else from homework? Yeah, Sam.
Number 60 on section 3.4.
Oh, yeah. All right. This one requires you to kind of go back to how to solve trig equations. In general, if I have some kind of sine or cosine function and I want to know where is the slope something, how many times will that happen? If the slope hits a certain value at some point, it's going to hit that value how many times? Infinitely many times, right? So this goes back to, remember how you had to solve trig equations and you had a plus 2 pi k, or if you're going to web assign, they want you to use n, but who cares what letter you put in there, right? It's just some multiple. So that's the basic idea of what's going on. So they give us 60, at least that's on first blush, that's what I think is going to happen. Sine 2x minus 2 sine x. And they want to know, where is this tangent line horizontal? So what does that interpret into in calculus? Making the tangent line horizontal means the derivative is 0. Cool. So I got to first figure out the derivative and then just force it to equal 0 and see what happens. So and one thing you could notice, well, it doesn't really matter for the derivative, but we'll see. We'll see what happens. What's y prime? What has to happen here? What's the basic rule I've got to use there? Chain rule. Good. There's a 2x inside of a sine function. Derivative of sine is?
Cosine.
Cosine. Derivative of 2x? 2. Cool. You'll start to get to the point, maybe some of you guys are there already, when you do sine and cosine, if there's something inside, some multiple of x inside, you just, every time you take a derivative, another multiple of that comes out, right? So the second derivative will be 4, negative 4 sine 2x, and then 8, and then 16. What's the derivative of this dude? Yeah, 2 cosine x. Cool. And you want to force that to be 0, right? To find the horizontal tangent line positions. So now it's just, do you remember how to solve this, right? And just to give you a little help, what I was about to say earlier is you could use a double angle formula there, or you could use it here. Now, which double angle formula do you like more? Do you like the sine 2x double angle formula or the cosine 2x double angle formula? And sometimes the one you like more is the one you actually remember. So I don't know which one of this is true. Remember the cosine 2x, what's weird about that one?
It goes cosine, cosine, sine.
No, careful. That's the cosine of the sum of two things, which is really where this comes from, but there's actually three ways to write it, right? The way I always start off with is this would be 2 cosine squared x minus sine squared x. And from here, of course, since cosine squared x is 1 minus sine squared x, then you could rewrite this as 1 minus 2 sine squared x. You guys, is this vaguely coming back?
Oh, yeah.
Right, so I just have this memorized, and then I can build the other ones really quick, right? Now, do you start to see why there might be an issue with, I mean, that's getting kind of gross, but I mean, so what's a better way to write this? What's the issue right now? When I'm trying to solve this?
You have a cosine and sine.
Cosine and sine.
Like if you just
That's no good. I want just
cosine.
cosine stuff, because that's the cosine out there, right? So how can I rewrite this in terms of just cosine?
2 cosine squared x minus 1.
I like it. And then you have a quadratic in cosine, FOIL it out, blah, blah, blah. It might even be factorable. I don't know. Let's see, 4 cosine squared x minus 2 cosine x minus 2. Yes. That's factorable. That's cool. All right. So you can factor that. You guys trust me? I mean, this is, and again, the trick sometimes is to put a c there instead of a cosine, so it looks more like, you can factor that, right? You can divide everything by 2. And this, 2c, 1, 1. You just got to figure out where the plus and the minus goes. Since the middle is negative, I want the bigger one to be negative when I do the FOIL, so that's got to be negative, that's got to be plus. Do you see that? Are you guys semi with me? Does this, right at this point, that's pre-calculus now, right? And you did exactly this kind of problem back in pre-calc, I can guarantee you. Right? And you're like, okay, that's nice, Jeff. It's been a while. But, oh well, that's how you do it, equals 0. So now you have 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. That's not too bad, right? Can you guys finish that one out? Is that? Are you guys here? Did you see the UFO earlier?
What?
There we go. Sweet. All right. I didn't see it, but maybe you did. I don't know if there was one. Just want to see if you guys are listening. All right. So, I think the point you got to remember is here, when you get this, what's the basic angle that makes this happen?
560.
Yeah, because cosine likes x. So to be the smaller output, it's got to be far away from the x-axis, right? It's got to have a reference angle of 60 then, right? And what's the 60 reference angle back here? There's pi over 3 away from pi, so it's 2 pi over 3. So this answer would be at least 2 pi over 3. Blah, blah, blah. And where's the other place where this happens? Where else is cosine negative 1/2? Where else is cosine negative? Third quadrant, right? That's another place where the cosine is negative. And it's also going to have a pi over 3 reference angle, so it's going to be 4 pi over 3. So what's this ... crap I'm doing out here?
Every time it hits the third quadrant, second and third.
So how do I capture that? Yeah, it's plus 2 pi k or n or whatever. And of course down here the same thing. And I always try to teach my students, the only time you can consolidate these two into one statement is if this distance was the same as the distance back around, and that isn't true right now. So you can't capture both of these answers using one step size because the back end, it takes longer to come back around. Does that make any sense? I think if you had me before, it makes sense because it's exactly how I explained it before. I'm not going to reteach pre-calc right now, so if you have a lot of trouble with doing this, but if it's just a little bit of I forgot exactly how this kind of thing works, that's how it works. Now, of course, you have to finish it out and do those answers. There's some more answers involved. From the very beginning, though, I could have written this original function as what? What's sine 2x? 2 sine x, cosine x. And then I could do its derivative. I don't know if that would be any better. You have to use a product rule here, right? So there's a decision to make in the beginning, and these should come out the same answers either way. It actually becomes this, as I think about it. Oh well, either way you do it, it comes out to that. Is that good enough, whoever asked that question? Okay. Any other questions from homework? Okay, all right. I'm an optimist. So that tells me homework is going great. There's one thing left from section 3.5. that implicit differentiation. So what I want to do is I want to do that one thing, and then I want to talk about section 3.6, and then I have a handout for us to work on. Yeah.
What homework, if we were like completely on track, what homework should we be turning into you today?
So last time we finished section 3.4 last time, right?
Okay.
So that would be this. Let me think. So that was Monday. So next Monday, if you have through 3.4 done, you're on track.
Okay.
Yeah. Does that make sense?
Yep. Perfect.
And remember, what's happening next Monday? Quiz up through what?
3-4.
Did I say 3.4?
Yep, you did.
Good. Listen, you guys, you had a chance. Yeah. Oh, it's the implicit that I left out. So it is through 3.4. Ah. All right.
There's a video to prove it.
What's that?
There's a video to prove it.
Yeah, I know. It's always good. Sometimes I'll look back to see, what did I say? It's really useful. Yeah.
Can you give an example of another implicit?
Yeah.
Yeah.
And actually, okay. So I'm going to take your question and turn it to my purposes. That's what I do sometimes. If I wanted to figure out this guy's derivative, and real quick, tell me what you remember about this function. Careful now. Does this mean the reciprocal of sine?
No.
Hell no. It means the inverse function. It means the sine has what as an input? Sine function has what as an input? What kind of thing physically do I put into a sine? An angle. I like it. So the inverse sine has an angle spit out, because that's how inverse functions work. You with me? So very quickly, what's inverse sine of square root of 3 over 2? Remember, sine likes y, so where is it going to be bigger when it's a bigger angle? So it's pi over 3. Right? So this is equal to pi over 3. So that's how I remember. Trust me, man. I don't have these memorized. I just take a second and remember, sine likes y, it's big, so it must be the bigger angle, pi over 3. If it was inverse cosine of root 3 over 2, cosine likes x. It's bigger when it's closer to the x-axis. That'll be 30 degrees, pi over 6. All right? Okay, cool. Or whatever way you want to memorize this stuff. More importantly, sine function looks like this. So how the hell is that ever going to have an inverse function? Exactly. So the domain that I wanted to restrict this to. You guys with me here? Does this sound at all familiar? Right? Why is that not going to have an inverse? Doesn't pass the horizontal line test, right? So I don't want to restrict it there because bam, it's already, it quickly dies. So I actually restrict it from here to there. And what are those points? Good, negative pi over 2? Pi over 2. So let me see if that helps out on this next quick question. What's inverse sine of negative 1/2? What's the reference angle going to be? Yeah, it's going to be when it's closer to the x-axis, pi over 6. But to be in the right quadrant, what quadrants is this really? This is quadrant 1, and this is quadrant 4. You guys with me? Quadrant 1 and quadrant 4. So that's positive-wise, negative-wise. There you go. That's why we had to restrict it to those, because that's how I get all those possible outputs. So the inverse sine of negative 1/2, since it's negative, it's got to be down here. Reference angle has got to be pi over 6. I get all kinds of neat things. So why is it 11 pi over 6? Yeah, because 2 pi is 12 pi over 6. Minus pi over 6 is 11 pi over 6. But that would be that. But what is it really directly? The beautiful thing is, what is it just directly? There you go. That's what I want here. Negative pi over 6. You can convert that into whatever to represent that angle. But if you did that in your calculator, which thankfully I didn't see anybody doing, which is awesome, it would come out with an equivalent of negative pi over 6. Okay, cool. All right, so that's a little review. So, of course, inverse cosine, where's it going to be good? Where's inverse cosine? Positive, negative? Yeah, first quadrant, second quadrant. So it's going to be 0 to pi. So that's the, and that actually relates to, remember the evilness with the, do this triangle, solve this triangle. And there's that one case where it was 2 possibilities because it was an inverse sine. An inverse sine just gives you a freaking reference angle. But when you did the law of cosines, you're fine. There was no possibility for a second case, right? It's related to how the inverse functions, how their outputs are regulated. You guys look really excited. Okay. All right, so let's get back to calc then. That's all pre-calc. Blah, 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 blah. How the hell would I figure out this guy's derivative? I really don't. Limit is 8. No. No, thank you. Right. So we've got, from section 3.5, we've got exactly the tool we need to do even more derivatives than we realize. I can build back to a function that I know by taking one of each side. I don't know inverse sine, but I do know sine. So if I take the sine of both sides, I'll get sine y equals x. Can you take this guy's derivative? Correct answer is hell yeah. What's the derivative of sine y?
Cosine.
Y derivative.
Y prime. That's a weird looking y. So now that we know implicit differentiation, we are allowed to mess with the function that's given to us and put it into a function that I know what it is. And then use implicit differentiation to get y prime. And what's the derivative of x? So y prime equals 1 over... Now that's not satisfying, because my function is a function of x. I want my derivative to be a function of x. Here comes some more pre-calc. Say again? No. What does this set up? That expression sets up what? And actually, from the beginning, it set up something.
Implicit.
And again, this depends. I don't know how you guys are taught in pre-calc. This is the way I taught my students. There's a whole other way to do this. But sine of y, so the y is the angle, equals x. So which side is x? What sine? Sine is what ratio?
Opposite of the hypotenuse.
I love it. Or y over h. Cool. So it'll be, this will be x, and this will be 1. Right? It's set up for me already. This is x over 1. It says sine of something is x over 1. Therefore, the appropriate sides from the ratio for sine must be x and 1. I want cosine of y right now. So, which side's going to be related to cosine? The one I don't know, of course. Right? When in doubt, it's probably the one you don't know. So what is this side going to be? Use good old Greek dude, right? Pythagorean theorem.
1 minus x squared.
Yeah, you got to be careful. Hypotenuse, big dude minus little dude, right? Square roots. The square root of 1 minus x squared. Whew. So then I get y prime equals 1 over, what's cosine of y? Square root of 1 minus x squared.
Do you have to rationalize the...
No, don't. Leave it like that, it's fine. So what did we just figure out? We just figured out that the derivative of sine inverse is this. Yes, sir.
Yeah, but what happens to inverse?
So it's don't forget, an inverse function is a function in its own right. I really want you to understand. It's the opposite of a known function, and you know, for the really, really basic functions, x plus 1, x minus 1, minus is the opposite of plus. It gets its own symbol. But when you got the sine, we said, I'm not going to make up a whole new symbol. Let's just be lazy and call its inverse sine. Ooh. Do you see what I'm saying? So what's the inverse of cube root? Cube. They get their own symbol and their own place to be. Poor sine, dude. His inverse is inverse sine. It's like we just got late. We're like, oh, we did enough shit already. Yeah. What's this inverse function? What are we going to call it? Inverse sine. That's creative. You guys with me? So that's a really good question, though. It's kind of like you see it explicitly, but that just is a symbol of a function. Inverse sine is its own function in its own right. It should be able to have its own derivative, right? That's why, I mean, that inverse is not really involved in the work. It's part of the symbol, like f of x, g of x.
Yeah.
Cool. Okay, so that derivative of that function is this.
Okay.
Cool. So you might be able to guess. So if this guy's derivative is this, what do you think this guy's derivative might be? Oops.
1 over the square root of 1 minus y squared.
1 over 1 minus x squared. Square root of 1 minus x squared.
So it can't be the same.
Same with negative sign, negative bracket.
So this guy's derivative is negative 1 over square root of 1 minus x squared. Which really is nice. Remember the whole thing from the basic 6 trig functions. The derivative of what things are negatives? The co-things. Right? So what's really, really cool about the inverse trig, one of the only really cool things about it is, if you know one guy, its co is negative of what we just did. And that kind of goes along a little bit with the basic trig functions. Now don't forget, I don't know if you guys remember this, I'm not going to make you memorize these. Unless you really want to. Because these are some, I just never took the time to memorize them. I just make them when I need them. Right? So if I'm somewhere on a desert island and I have to figure this inverse trig derivative out, and I don't have a thing to look at, I just figure it out myself real quick. Well, we just did. Right? And that hasn't happened yet, but I'm sure that's what I would do. It's a very strange reality show. Oh, so if you look on page, just to cut to the chase, you can do very similar things with the other trig functions. So the derivative, if I have tangent inverse, its derivative is going to be 1 over 1 plus x squared. If I have cotangent inverse, then what do you think its derivative is? Yeah, negative 1 over 1 plus x squared. And then secant and cosecant, you can read them there. I'm not going to write them. Page 214 at the bottom. So if on a test you're going to need them, I will have them somewhere for you to reference. Yes, ma'am.
Page was it?
Page 214. On a test, I will very likely make you rederive one of these things. So it's not a bad idea to try to derive it yourself at some point. Okay, so any questions over those? Okay. So that was the last thing out of section 3.5 that we had to talk about. And Liz, I have a feeling that was probably not the best example of implicit that you wanted. So let's do, well, there's going to be examples here in a minute. We'll do this group work thing. All right, so let me finish out. Let's talk about 3.6. Natural log of x is a weird dude. And help me out here. If I had y equals x to the third, y prime is x squared, y double prime is 6x, y triple prime is 6, y fourth derivative is 0. See how there's no bridge? How do you get to, once I get to the, if I had y equals x to the negative 1, what's y prime? Negative x to the negative 2. Y double prime would be, good, 2x to the -3, I mean, so forth. So it looks like it wants to continue doing what this guy started. But what's the connection? This guy dies before it gets to the negative powers, right? 0 comes along and screws up any chance of that being the bridge. So somewhere's got to be a bridge. And maybe that might be why I'm saying all that. So how would I take this guy's derivative? I have no idea currently what the derivative of natural log is. Right? In this class we don't. So what would you suggest I do? Maybe based on something we just did.
Power for
Good.
E, use the 8.
E, right?
How do you rewrite this?
But you raise it to the 8.
X equals, yeah, e to the,
1 of 1.
right? Is that cool? That's how I rewrite from log form to exponential form. So just like we did with the sine. We had inverse sine. I had no idea what the hell it was, so I just did the opposite, and then I get a function I know what the derivative is. Same thing here. I don't know what natural log's derivative is. It's the whole purpose. That's what we're doing right now. So we rewrite it in terms of a function I do know, and implicit differentiation comes along and saves my ass. So how do I implicitly differentiate this? I'll do this side. Yay. That side's not too hard either, is it?
E to the y times y prime.
I love it. And e to a gets itself, then the inside gets a turn. So then y prime equals,
E to the fourth, actually E to the y.
1 over
1 over,
E to the Y.
and what's e to the y?
E to the Y. X.
X. So y prime equals 1 over x. So the derivative of ln of x is 1 over x, which is x to the negative 1. And then that would start off that whole chain of, and then the second derivative would be negative x to the negative 2. And that would do that whole chain. Are you guys semi with me? Yeah, okay. So that is now and this is definitely one you have to memorize. In fact, if I don't say you need to memorize it, I will tell you the ones you don't have to memorize. But this is easy. You've got to know that natural log of x goes to 1 over x. Now, what's one problem? Anytime we talk about working with the function and doing something with it, I kind of need to pay attention to what x really represents. What is one major difference between that function in regards to x and this function? How they can work with x. I'm not sure how to put that question without giving the answer. There's a huge difference between what this guy can do compared to what this guy can do.
X can be 0.
And neither one can x be 0, right? So that matches. Where does it not match? Yeah, ln can only handle positive values, whereas this officially would be able to handle all of them. So if I had a problem that had y equals ln of x, it inherently means that this can't be negative. Because I started with a function that could only handle positive inputs. So let's try something out. Let's kind of build our way up here. Take this guy's derivative here. What are you going to have to use to do it? Chain rule, I love it. Do you see how we keep learning new derivatives, but the basic rules, chain rule, product rule, course, they don't care what the hell functions are in there. They always do the same thing. Then we worry about those individual derivatives and how they work. Right? Something very funky happens here. I love it. All right, so y prime. What's the basic definition of ln of something? It becomes 1 over that thing. You with me? E to the x's derivative is e to the x. But e to the 2x's derivative, the first thing I do is e to the 2x. The idea of e's derivative is it stays the same. The idea of ln's derivative is it's 1 over whatever the hell's in there. So that's 1 over 2x times 2, the derivative of the inside dude, right? So that's chain rule. So the rule for ln is when you take the derivative, it's 1 over u. And u being whatever the hell is in there, function of x. times chain rule piece. Right? What happens? 2's cancel, y prime equals 1 over x. So if I would have done ln of a billion x,
1 over.
the derivative would have been 1 over x. If you think about that, that is really kind of funky. This represents what? Slope. So the slope of the function doesn't care what constant is in there. Sounds to me like I would want to look at those graphs and see why the hell that's true. But it's a very interesting point. So if I put like an a in there, I mean the same thing would happen. I go 1 over ax times a. The a's would cancel. So I mean that means whatever that constant is, it doesn't care. Okay. You with me so far? All right, here's the next thing. What about this guy?
Two over.
1 over x squared
To start with.
times 2x.
Right. So you could do the derivative of ln of something is 1 over that thing. Then that thing gets a term. The derivative of x squared is 2x. And when you reduce that, you get 2 over x. Now, let me make this point right now and save you from yourself. I can simplify logs quite a bit, right? Using the log of the product is the sum of the logs, and the log of the quotient is the difference. And that sounds really important. If I had a log of a quotient, that's a chain rule, quotient rule matchup that I would rather not have to do. And thankfully I don't. The log of the quotient is the difference of the logs. And that's a much easier derivative. So I think when I taught my pre-calc class the properties of logs, I was trying to say that those will be used in calculus to make some calculus stuff easier. You guys are there now. So I could have done what with this? Brought the 2 out front. That is damn easy. 2 times 1 over x. Done. Right? So you can use properties of logarithms to simplify the function first, make it easier to do the derivative. Yeah.
So when you did it the first way though, why does the squared go away?
Oh, it canceled with the x that was there, right? What's the derivative of x squared?
Right, 2x.
So 1x cancels, yeah.
Gotcha.
Cool. Okay. So now we're able to maybe tackle this thing. This is important to talk about because when we start talking about the opposite of differentiation, so you have to realize that taking derivatives is itself some kind of function. It's an operation that we apply. There is an opposite operation. And there was a bonus question on the first test that was basically asking you to go backwards. Where did this derivative come from? And you had to think backwards. Right? So when we get there, what we're about to do is going to be very important to realize. What the hell do I do with absolute values? I mean, what's the derivative of an absolute value? What do you do?
Make it down to positive x and negative.
Okay, so you can make this into the form of a
Positive,
piecewise function. So this will be natural log of x if x is greater than equal to 0. And this is natural log of negative x. It's got to change the sign if x itself is negative. Right? So to take the derivative, I just take the derivative of each piece. So let's see what happens. Now, of course, here that's just strictly greater because it can't even handle 0. So what's y prime? So this top part's easy. 1 over x. And what happens in the bottom part? Yeah, derivative of ln something is 1 over that thing, but then the inside derivative is negative 1, so those negatives cancel. It's still 1 over x. So the derivative of ln of the absolute value of x is just 1 over x. And I really want you to see, does that tie in with what I was saying earlier? If I just say natural log of x, I have to assume that x is positive. I've lost half of my poor little 1 over x picture. You with me? If I say ln x, I have to assume x is positive. Its derivative is 1 over x. But I can't use this side of the picture, can I? But if I say ln of absolute value of x, now and the derivative is still 1 over x. It doesn't care. Natural log doesn't care. You can do a lot of weird things to this and it doesn't care. We saw it with a constant. Then I can use both sides of the picture, because now it doesn't matter if x is negative from the beginning. I don't have to exclude it anymore. So in general, real quick, if I said y prime is 4x, what would y have to have been? Just to give an example of this before I hit this.
X to the 4.
Definitely
X
not.
squared.
Yeah, it would have to be. And x to the first would have come from x squared. A 2 would have come down, so there must have been a 2 out there. You guys with me? Now, when we get to the point where we start talking about anti-differentiation, which is the opposite of derivatives, we'll make that rule more formal. Right now, I don't care. So in the future, when we see this, and I say, where did this come from? We have to say that. Because is there any restriction on x in this statement? No. Except for 0, right? X can't be 0. That's given. But it can be positive or negative. So when I take the derivative, when I undo the derivative, it still has to have that. It still has to be able to handle all the x's. So I have to say that. And this is why it works. Because it doesn't care if it's in there. It's still 1 over x. So no big deal. You can do that. Because it really is just a multiple. And any multiple, it'll kill. All right, that's way more than I want to say about that. That's plenty. Okay. So any questions on any of that? So I really want you to realize, and this kind of thing happens all the time in math, we learn a new function, but the old property, the old processes don't care what that is. They still work the same way. So product, root, quotient, they all are in effect for natural logs and inverse cosines and all that kind of crap. All those rules still work the exact same way. It's their own individual derivatives that you have to know what they do. Right? Okay, so here's what I did. I just remembered how I did this. I have the answer key for this, copies. But to save some paper, I'm going to put this up here. So what I really love is if some of you guys feel free to work in groups on this. If you want to work by yourself, that's cool. Call me over if you need some help. So this is going to incorporate natural logs and inverse trig stuff. Can you guys all see that okay? So your first step can always be simplification of some kind. If there is something you can do to make the derivative easier to take, do it, right?